lesson 2 is called factoring. We're going to factor polynomials, and then we're going to work on factoring theorems and then solving equations that will need these skills that we're going to build upon. So first, like usual, at the beginning of a lesson or beginning of a unit, I will do quite a bit of review. For those of you that haven't taken pre-calculus, yeah, it's a lot, I know. And those of you that have taken pre-calculus might be a bit bored, but we're gonna do that in adult ed. So, what is factoring? When factoring a given expression, you are going to be changing the expression from a general form, the one that we've seen last class, that has power terms that are added and subtracted, into a form that now has factors. You're multiplying two pieces in which either you have a monomial and a binomial. You can have binomials times a binomial, or you can have, again, combinations of monomial with other kinds of polynomials, or you can have polynomials times a polynomial. But in the end, you have two chunks that are multiplied that are not monomials. Okay, they're not just the powers that multiply, because that in the end is just going to be another kind of monomial. Okay, so you're changing its form from having addition subtractions of various terms. Remember, our terms look like that. The power terms, a times x. I put square there just as an example, to a multiplication. Except monomials. So, for example, instead of writing 2x plus 6, I can write the same expression. So that's a very key idea here. You're not changing the expression, you're just changing its form. It still equals the same thing, okay? We can change it as 2 times, and in the bracket, I'm putting x plus 3. Okay, now these two expressions are exactly the same. But this one has just terms that are added, 2x plus 6. This one has a monomial now, which is 2, and times a whole binomial, a whole bracket, okay? This idea of the multiplication, that's called factoring. Going from here to here, you factored. What did we factor? Well, we factored what we call the common factor, the greatest in this case, the greatest common factor, GCF, out of these two terms, because here I have 2 times x plus 2 times 3. So 2, we said, is a common factor in both of those chunks that are added. Make sense? And then we can extract it out, write it only once, and that's called the factoring. You pull it out, the common factor, and then you are going to be leaving in the bracket what's left out when you pull out the 2. Go ahead, Paul. Yeah, we're going to talk about that right away. That's common factoring. Okay, so now greatest common factor, we're going to cover that. This kind is one of the simplest kind of factoring that you start with when you're learning factoring in grade 10. The greatest common factor is the largest factor that divides all terms in a given expression. So for us, in this example, was 2, because 2 was the number, the factor in this case, because it becomes multiplication. The factor divides both 2x and 6, right? So when you find something like that, you just write it once, you open a bracket, and then what you put in the bracket is the answer to those divisions. So here I divide by 2, I'm left with x, I put the x there. I divide by 2, I'm left with 3, and put the positive 3 there. And that's how I figure out what goes in the bracket. So first you find it, you choose it, which one is in both, okay? And then you divide that number by both of those terms, into both of those terms, and then you get them to go in the bracket. Let's do one more. factor the GCF in the following polynomial. So GCF means the greatest of these kinds of numbers. So everything that you can extract, you must extract, right? So 15x squared minus 3x. You can search for a number common factor and a variable common factor that you can divide both terms by. So let's start with numbers. What number divides both 15 and 3? 3, right? So that's the part that's the number factor. And what x divides both x squared and x? X, okay? So it's always going to be the lowest version. And now you can open the bracket like that. And now in the bracket, it's going to be the answer of these divisions. So 3x, now you put it into 15x squared. What you're going to be left with is 5x. Negative 3x divided by 3x is negative 1. Now, last class, what we've done is going from here to there, from the factored or multiplication version to that version, because we learned how to do distribution, right? And we did FOIL and all that. So 3x times 5x gives you back the 15x squared. 3x times negative 1 gives you back your negative 3x. They're exactly the same expressions, just written differently. Now, you may think, why do I need to know that? Because when you have a fraction, for example, like this 3x over 15x squared minus 3x, and you want to simplify it, okay? 3x at the top, and then we already saw that 3x is the common factor, 5x minus 1. Now, the only way you can cancel things top bottom into an expression if you have multiplication. Okay, so I can cancel this x from here with that x from the 5x. It's not allowed. But I can cancel 3x entirely with the 3x from here because I have times right there. So you can only cancel factors, but not chunks that are added and subtracted. Clear? Okay. So that's why you need to learn this skill. And then you'll be left here 1 over 5x minus 1. Okay, now some situations require you to factor not the greatest common factor, but just a number. And we will see some of them later on. So in example 2, we're going to practice this skill. From each of these following polynomials, we're going to factor out the specified value in the braces. So from the expression 9 minus x squared, I'm told take out negative 1. There you go. I took out negative 1. All I have to do is rewrite it in the bracket, what's going to be left. So 9 divided by negative 1, because that's what I'm doing in my head. I'm not going to keep writing this every single time. Some of the, at one point in time, I'm going to not show this work. So 9 divided by negative 1 is negative 9. And then I also will divide by negative 1 here, and I'm going to get plus x squared. X squared is negative, negative 1 also negative. So 2 of the same signs that divide, it's going to give you a positive sign. And then I may be wanting to rewrite this one a little bit nicer, because for some reason we like to not write 1, okay, so just the negative. And we also like to start again with the highest exponent if I have a polynomial and go in decreasing order of exponents. So I would go x squared minus 9 in that order. Is this required? No, but it's kind of a convention that everybody does it. And a similar thing for B, we are told that from negative 6x minus 4, I'm told to take out a factor of negative 6. So I don't have a choice here. I'm not figuring out what's the GCF. I just want to take out negative 6. So then the first term is, let's see if you got this. In the bracket, the first term will be, that's right. And then we're not going to write 1. We're just going to write just x, okay? And then plus, again, 2 negatives. 2/3, because if I divide by 2, I get 2 and I get 3 there, right? So 2/3. You can always check your work when you work with fractions, multiply back and make sure you get back the 4 there. Right, so 3 and 6 cancels again, and you get a 2 there. 2 times 2 is 4, okay? And that can stay like this. Your turn, 2.1. Remember, I gave you keys for these ones. Okay, I gave you a booklet that has solutions. So make sure at the end, when you're doing practice questions, you check your work, check your answers with those keys. Oh, any questions for factoring before I move on? You good? Yeah. Make sure you ask if we have a break or something and you get started on your turn, you can definitely ask me questions, okay? In between as well. Okay, so factoring quadratic trinomials of the type ax squared plus bx plus c. And we notice that we have this a here. It's going to be 2 types of these factoring. Where this a is 1, basically you're going to have nothing there, or when a is different than 1, when we're going to look at this this page. I'm doing the one that's a little longer method first, because actually this method works for both situations. Just that the other one, the second one that's following it, it's going to be more of a shortcut. So if you notice it, you should be using the shortcut because you're not wasting any time with this longer method, okay? But this is the method that it's sort of showing you how to get to the other methods as well. It's the main thing. So when you have trinomials where the leading coefficient is not 1, we can factor it. We may be able to factor it. If I multiply the leading coefficient with the free term, I'm getting a number. If I find 2 factors of that number that add up to the middle coefficient, then I can factor it. If I cannot find those factors, then the trinomial is called non-factorable. I have to leave it the way it is, okay? Now, a lot of mumbo jumbo there. You probably lost me in the explanation, so let's see how that looks like. So the way you decide if you can factor this polynomial, 9x squared minus 3x minus 2. See how you have here a number in front of the x squared different than 1? It's 9, right? The way you can check it is first take the 9 and the negative 2 and multiply them. So multiply a and c. So 9 times negative 2, let's put times like that, is negative 18. And now you check to see if you can find 2 numbers, 2 factors that multiply is negative 18. And then add it, it's going to give you the middle term, the negative 3x. So the versions could be the following. Factors of negative 18. I can do negative 1 times 18, right? That's a good combination for factors, right? That's true. One piece is true. Negative 1 and the number 18 are factors of negative 18. But when I add them, I have to always check. If I add them, these 2 numbers, are they giving me negative 3? No, right? So even though they are a pair that works for factoring, it doesn't work for the addition. We sometimes call this method as multiply method. You might have learned it like that when you were in high school. Okay. Now, another combination of factors, because there's more possibilities for 2 numbers that multiply that give you negative 18. For example, negative 2 and 9. Agreed? If I check again, if I add negative 2 and 9, I get what? 7, right? It's not negative 3. This is also not a good pair. Okay, so cross it off. No good. So in your mind, you look for those factors. If you find a pair, you can continue the method. If you can't find it, okay, because you checked all the possibilities of the pairs, then you can conclude you can factor it, right? But this one is factorable, obviously, because I'm trying to show you the method. So the pair that works is negative 6 times 3, right? Negative 6 times 3 is negative 18. So they are the factors of negative 18. When I add them, Okay, I get -3, which is the middle term. So these are the good factors. Yes, I found them. Make sense? So this trinomial is going to be factorable. I will be able to write it as a multiplication of two binomials. That's what we're going to go towards. Now, how does it work? I rewrite the 9x squared minus 3x minus 2 as 9x squared minus 6x plus 3x minus 2. Who's going to tell me what I've done? It's still the same expression, but it's a little bit different. What did I do? Sorry? Not quite backwards, no. I still have the 9x squared here. I still have the -2 there. Well, it's okay, Paul. It's good. Thank you for the answer. We will do grouping in the next step, but what did I do here? I took the -6 and 3, the pair that we just found, and I used it to split up the -3x, right? So it's still equal to -3x. I just wrote it as two separate terms. So -6x plus 3x, it still gives me -3x, but I wrote it like that because in the next step, I'm going to group it, okay? So now I'm going to take these two, find the common factor, the greatest common factor, and I'm going to take these two and find the greatest common factor there. So two groups you'll have. Okay, so now let's focus on the first group. What's the common factor between 9 and 6? 3. So 3 goes there. What's the common factor between x squared and x? X. And then we're going to put something in the bracket. So we grouped these two and we factor in that group. We are left with 3x and then -2. And so this is, this is the first one, okay? We've done the first one. So in the first group of two, we factored out the GCF. Is it clear? I haven't done anything with the second group yet. Now in the second group, you factor out the GCF. If there isn't any GCF, you put 1, because it's going to be easier for you for the next step. If there's a negative in front of the first term, factor out the negative as well, okay? This one only has a positive. So we're just going to put +1, because there's no common factor different than 1 there. And then bracket, we're just going to copy the same thing, right? Now I'm done the second factor right here in the second group. So 1 is that, the 2 is that. Is that clear? Okay. Now when you reach this step, you have to have the same bracket, because now this bracket, it becomes the GCF of this bigger expression. Okay, it's like the 2 we just learned like the previous page, right? So now this one comes in front as a common factor, this green bracket, 3x minus 2. And what goes in the second bracket are these pink ones, 3x plus 1. Notice how we have two binomials that are multiplied. So we went from addition, subtractions of terms to a multiplications, in this case, of two binomials. Go ahead. Yeah, I think we have a few more examples to go over. Yeah, so we can we can practice a little bit more. What is going on?
The step 2.
Step 2.
So we're using the 5.
Okay, step 5.
So like the ones inside the brackets, the answer like 3 divided by 9.
Yes, these one in the bracket, that's these are the answers where you divide by 3. So what we did here is basically what we learned with the 2x minus 6. So what was that example? That's what we just factoring out the GCF. So we reapplied now the GCF on page 19 in example 1, and when we factor out the GCF. So it has to be, that's the most basic kind of factoring, and that you'll see every now and then in other types of scales. All good?
Yeah.
Okay. Now let's practice this method a little bit more. So factor the following trinomials. The first step you do, okay, you notice it's a trinomial, quadratic, it's a squared here. Okay, that's very important too. It's quadratic. So then you take the 2, you times it by the -6. 2 times -6 is -12. And then you're trying to find factors of -12 that add up to the middle term. The middle term here has a factor -1 in front of it. So -1 times x. So what's two numbers that are factors of -12 add up to -1? -4 and 3. If I add them, do I get -1? Yes, okay. So these are it, okay? And you're gonna use them with an x beside them to split up the middle term. So I could just put equal here. 2x squared stays, -6 also stays. So instead of writing -1x, you're gonna write -4x plus 3x. So you don't write this term anymore. We'll just rewrite it like that. It's the same thing. It's like terms we learned last class, but backwards. And now we group them 2 by 2 and factor out GCF. This is the first group. That's the second group. It doesn't matter in the end. You're just gonna end up with your two binomials backwards, but it doesn't matter. You'll get exactly the same answer. Yeah. So sometimes it's just easier, depending where you put it. It just looks nicer. So in the first group, we can factor out 2x, and we're gonna be left with what? 2x minus 2. Okay, and then in the second group, is it 2? No, 2 there. X minus 2. And then in the second group, I think we're gonna have to go and close that door. Because it's, but thank you, Paul. Would you? That would be great. Because then I think we're gonna have a bit more peace. So that's the second group. We can factor the 3 out from the both terms, 3, and then we're left with x minus 2. At this point in time, and this is how I noticed right away, this one was wrong here, because you have to have the same bracket, right? Because now this bracket is the common factor, and that goes to go in front of another bracket. So we can write equal here, and then x plus 2, and then open another bracket, and inside you just take these two terms and put them right there. So 2x plus 3. Right. So here, if you're putting 3x first and -4 second, these two brackets will be backwards. But it's the same thing because multiplication is commutative. 2 times 3 is the same thing as 3 times 2, so it doesn't really matter. Okay? So x minus 2 times 2x plus 3 is our final backward version. Let's try again. 3 and then 2. We take these two. 3 times 2 is 6. 2 factors for 6 that add up to -5. So let's try. 2 and 3. With the goal. It's 5. No good. 3 and 2. 3 plus 2 is 5. No good. We want -5. -3, -2 is 6. If we add, it's 6 multiplied. If you add them is -5. Agreed? Okay. So here's always you add them to check the middle term. So now we put the x beside it like that. And we're gonna replace the middle term with those two. You're so loud. 3x squared, I can't even focus here. Okay, 3x squared minus 3x minus 2x plus 2. You see them there in the middle? Okay. Now 2 by 2. Factor out the GCF. In the first group, the GCF is 3x. And then we have x minus 1. In the second group is 2, but if your first term is negative, take the negative with it, okay? If the first term is positive, take the positive with it because it's going to show you how to connect the terms, okay? So negative 2, and then x minus 1. And then you see how the bracket is the same. That's now becoming one-time bracket, x minus 1, and then 3x minus 2 goes from the second one.
No matter which bracket.
No, it doesn't. But I would always start with the factor first. But in the end, it doesn't matter if you have them backwards. You can start with 3x minus 2 and x times x minus 1. It's fine by me. And now the easier factoring. When you have a quadratic trinomial where the leading term is 1, basically you're not going to see anything like all of these examples. See, it's x squared, x squared, x squared. There's no number there. That just means it's 1 times x squared. In those situations, we may factor it in the form x plus, I think I use h and k, x plus the k like that, where h and k are the factors of the free term. So if you find 2 factors of the free term, again, add up the middle term, you can go straight here. You don't have to go through the long method. You still can if you want, but why would you? Okay, because you can skip steps with this method. Okay, now I'm not going to go and show you the method just yet. I want to show you how it works with the previous one and how it is longer than the one that we're going to do. Okay, so just pay attention. Don't do anything for this one. X squared plus 7x plus 12. This is 1. So 1 times 12. 1 times 12 is 12. 2 factors of 12 that add up to 7 are 3 and 4. So 3x, 4x. So we have x squared plus 3x plus 4x plus 12. First 2, second 2. So we get an x from there, x plus 3. We get a 4, a positive 4 from there, x plus 3, right? And you're going to go to x plus 3 common factor. And in the other bracket, x plus 4. Oh, guess what? What are these two numbers? Right? Just positive 3 and 4. So why would you go through all of that when once you find them, you can skip all these steps and go from here straight to there. Make sense? Well, let's practice to see if it does make sense. So what are 2 factors of 12 that add up to positive 7? Is 3 and 4, you said, equal to brackets. You're going to have an x in each bracket for these ones. And then whatever you see as your factors, those are the signs inside the bracket. So you see positive 3 here, because that's your factor you found, it's plus 3. You see positive 4 there, it's just plus 4. Done. Way faster, right? So when you get one of these, you're happy because you have to do the long method of factoring. Now for x squared minus 8x plus 15, you look at 15, positive 15, 2 factors of positive 15 that add up to negative 8. Let's try it. 2 factors, 2 numbers are multiplied. They have to multiply first. Negative 3, negative 5, multiply to give me positive 15. When I add them, I get -8,
I see.
right? So that checks them. So first you find them because there's different versions of factors. And the way you check to see if it works for this scale, you see if they add up to the middle term. If they do, then you go now to factoring. X in each bracket. And then you just copy them in there. -3, -5. Again, it doesn't matter in which bracket you put them. Now, if you go back and check with foiling from last class, multiplication of binomials, you should get back your trinomial. Okay, -40. Two factors of -40 that add up to -6. -10 and +4. So you see how you multiply them, you get -40. Now you have to check. Does it work? Is the right pair this one? Because not all of the pairs will work. Only one pair will work. So add -4 plus -10 plus 4 is -6. So that means it's a good pair. Then you just go straight to factoring. -10 plus 4. -5. -6 and 1 is not, they're not factors of 5. I know. This one is the trap one. Okay. So -5 and 1 are factors of -5, but it doesn't work because -5 plus 1 is -4. We want +6.
What do you think the best way of keeping that fund that?
There's no best way. You just have to like do factor trees if you want, if it's a big numbers. Yeah, find a way that they multiply and give you that answer. But if the number is big, you can do factor trees, kind of split it up into small numbers and then do some combinations. But yeah, usually I'm giving you pretty like good numbers to work with, not like really, really big ones. So what are the options we have for 5? Because 5 is a prime number. It only has factors itself and 1, right? So you can only do either -5 and 1, or you can do +5 and -1. Does that work? Does that combination work? No. And then you're done. There's no other factors for 5. Okay, that's it. Make sense? But you do have to go to the list. If you have, for example, 6, you have to go 2, 3, 3, 2, right? Or like if it's like -6, for example. And then you have to do 1, 6, 1, -6, and then -1, 6. In a case when you solve equations, yes. If this question is only asked you for factor, you just say it's not unfactorable, non-factorable, prime, quadratic, trinomial. All of these versions are the same to pretty much answer. So you can say simply cannot be factored. Right, that's it. Okay, so let's take a maybe 10 minutes break. So 2:20. About 10 minutes. 2:20, you can come back. If you're taking off all of the factoring methods that I've shown you up to now was either from grade 10 or from grade 11, pre-calculus. Moving on from now, these are all factoring theorems from grade 12. This is all new for everybody. Clear? Up to now, not new. From now on, it's all new. So we are going to start with the remainder theorem. This is a theorem that's going to show us if we divide a certain polynomial by the binomial x minus a, how can we quickly figure it out if that binomial x minus a is a factor, divides it completely, or actually have a remainder. So it will tell me what the remainder of that division is. Is it 0, meaning it's gonna divide completely, or is it actually a number, meaning it's gonna have a remainder? Okay, so When a polynomial p of x is divided by a binomial x minus a, where a is an integer, integers are these numbers, dot, 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 -3, -2, -1, 0, all the way to positive infinity like that. The remainder of this polynomial division would be p of a. Well, the calculation, I think I have actually words explanation for this one. Let me see. Yeah, the calculated value meaning, what does it mean, calculated value of PA? It means that we're going to replace all of our x's in the polynomial P of A with A and just calculate to see what we get. So the remainder is calculated by replacing all x's in a given polynomial with the value of A. The way we're going to get the value of A, it's going to be the same way we took it for synthetic division, always opposite the way you see it in the binomial. If it's x plus 2, a is going to be -2. If it's x minus 1, a is going to be 1. Okay, the reason why that happens is because you have that x minus a in front of a. So whatever comes after it is always opposite sign. Clear? Okay, so let's do example 5. Find the remainder of the following divisions without using long or synthetic division, because obviously you can find the remainder like that, right? Doing the actual division. So we have 3x squared minus 2x minus 6. This is your p of x. And this is the binomial x minus a. So to find the remainder, all you have to do is p of what? What's the a? -1. So we look at x plus 1 here. We take the opposite of that number, and then we replace -1 everywhere we see x in the given polynomial and then calculate it. So we would have 3 times -1 squared. So instead of x, I put -1 minus 2 times -1 and minus 6. All of these were x's before. And we calculate BEDMAS, right? Powers first, and then multiplications, and then additions and subtractions. The first one is -1 squared, which is going to be +1, right? -1 times -1 is +1. Now here I can already do multiplication. -2 times -1, which is +3, and then -6, I'll just copy. +2, that's right. Thank you for that. Okay, and now 3 times 1 is also a multiplication, 3. And here I can do the addition of 2 and -6. So 2 plus -6 is -4. And now finally 3 minus 4 is -1. That's the remainder. Same thing for the B part. It doesn't matter if it's not in the right order for this one. It's not an algorithm where they have to be in a specific place at the start. So for this one, all you gotta do is notify or is noticing that you have to divide this by an x minus a binomial. This is x minus a. And you are asked to find the remainder without the division. What is the a binomial from this one? Not -4, but opposite that, okay? You want what comes after negative, which is +4. So everywhere we see an x, we're gonna replace it with the 4 and calculate it. -4 to the 4 minus 2, 4 squared minus 1 plus 4 minus 4 cubed. Okay, now I always tackle BEDMAS, meaning the order of operations, starting with the powers. If I have a multiplication, I do the power first. If I only have a multiplication, I can definitely just multiply and then just kind of reducing that calculation one by one when I can, but in the order of operations, because that always has to apply. So here I would have a multiplication because we have -1 times the power. You would have to evaluate the power first before you multiply by -1, right? So I would do negative and just figure out what the 4 to the 4 is first, which is 256. You can use a calculator for these ones for sure. And then I also have a multiplication here, -2 times this power. I will do the -2, figure out the power, which is 16. -1 plus 4, you can combine them if you want. -1 plus 4 is +3, right? And here you only have a power, so -1 times the power, which is 4 times 4, 16 times 4 is 64. And now we can take care of the signs and some multiplications here. The negative in front of the 256 stays, -256. -2 times +16 is -32. And then 3 and -64, if you want, you can combine again, -61. 3, -64. So we can see we get a bigger negative because all of them are negative numbers, right? So basically just add all of those ones and just don't forget to put the negative in front at the end, right? So what are we gonna get? -349 is the remainder. So you're getting the remainder with this theorem without doing the actual division. Okay? Now here's an application or different kind of question that uses the factor theorem. What is the value of a in the polynomial x cubed plus a, this is the a they refer to, minus 5x minus 6, if when divided by x minus 1 gives a remainder of 2. So when you have a question like that, that talks about the remainder, because you're doing polynomial theorems, you got to remember you've learned a polynomial theorem that has a remainder solution. So you can basically write all of the givens of this question and the question by writing what we know about the remainder theorem. So we know that if I divide the polynomial p of x by x minus 1, I can find the remainder, how? By doing p of one. And what is the remainder? Because I also know that if I do p of 1, because that's the one I'm taking this from, right there, it goes there. If I apply the remainder theorem, I know the remainder of this division should be -2, right? So now I'm going to focus on this part. Do I know what p of 1 is? Maybe not directly, but I know what to do, right? I can replace all of the x's with 1 in the original polynomial. And I know that once I do that, that calculated value should give me -2. So here I have 1 cubed. Here I have plus a times 1 squared. Here I have -5 times 1 minus 6, and I know it has to give me -2. Now the only thing that's missing in this expression is the value of a, which is what the question was asked for. The question asked us for, it was, what is that a that's missing over here in front of the x squared? So let's see if we can find it. It's just an equation solving. Do you know which kind of equation? Linear equation, right? Because the missing value of a is a to the power of 1. So it's a linear equation. So 1 cubed is 1, 1 squared is 1, 1 times a is just a. Negative 5 times 1 is negative 5, and I'm copying negative 6 equals negative 2. Just copying it over there as well. Now we're going to put the like terms together, all of these numbers. We have 1 minus 5, which is negative 4, right? And then minus 6, negative 10. So a minus 10 equals negative 2. Now we want to move the negative 10 on the other side, or in other words, we want to cancel the minus 10 by adding 10 to both sides.
What did you want to say again?
I put all of these together.
Oh, I see, okay.
Yeah.
Yeah.
So if we add 10 here, we're going to get 0, and then we have to repeat that on the other side. So a on the left-hand side is the only variable left, and 10 minus 2 is 8. So the missing a value is 8. A lot of questions like that in this unit, so just remember the application of these theorems. Factor theorem. So this is just an extension of the previous theorem. Like I told you, the remainder theorem, if you get a number as your answer, then you have a remainder. But if you get 0, that means that division is complete. You don't have a remainder. Okay, and that's what this theorem is all about. A binomial x minus a is a factor of a polynomial p of x if and only if P of A, which is the remainder theorem calculation, must equal to 0. That means you have no remainder. And when you have a polynomial division that has no remainder, one of the forms we have learned for it, right? So if you have those division statements look like this: P of x divided by d of x equals q of x plus r of x divided by d of x. So when your r of x, your remainder, this one is 0, the whole thing disappears here, right? So when we say it divides completely, you're only going to get an answer, the quotient, and that's it. Make sense? The other form that we had for the second division statement was like this: P of x equals q of x times what we divided it by plus r of x, right? When you have no remainder, you don't have that, right? So what you're dividing by the d of x, let's call it a factor of the polynomial p of x, because you don't have a remainder and the division is complete. Okay. Okay, so let's verify that x plus 1 is a factor of each of these given polynomials without using long or synthetic division. So how do we verify for the first one? Well, we have to check this -1. So we're using another name than p of x. We're using a of x for part A. So we have to check a at -1. We replace every single x with -1. -1 squared minus 2 times -1 minus 3. And we calculate to see if it's 0, right? If it's 0, then we can say x plus 1 is a factor, divides completely. If it's not 0, then it's not a factor, and that's it. So we get -1 squared is 1. -2 times -1, it's not -3, it's +2. And minus 3. Equal 0, right? So we can say x plus 1 is a factor. Basically, then you can write a of x as x plus 1 times whatever q of x is. Without the division, we don't know what the answer of that division is. This is missing right now. But we know that is a factor. So it would be x plus 1 times something else. Since our a of x is a quadratic, this q of x will be a linear because you already have a linear in the other factor, right? So linear times a linear would be a quadratic. So it's very likely you have another binomial in there for q of x. Okay, maybe that's a little bit advanced, but it will click at some point and you'll see what I mean. P of x is x cubed plus 2x squared minus x minus 2. We want to see if the binomial x plus 1 is a factor. What do? We just check the negative 1 right in it. So we have negative 1 cubed plus 2 times negative 1 squared minus negative 1 minus 2. Negative 1 plus 2 times 1 plus 1 minus 2. Negative 1 and 1 is 0. I like to sometimes cancel them like that when they equal to 0. Here I have a 2. And here I have a negative 2. So these ones also will be 0. So equals 0. So we verify, right, that x plus 1 is a factor. If I would do the statement for the division, P of x will equal to x plus 1 times q of x. Again, no remainder, because that's what it means by being a factor. And I don't know what q of x is, but I do know what the degree is, because I'm dividing by the factor that's a linear, and I'm starting with a cubic. So if you divide a cubic, which is x cubed, by x, what's going to be the degree of q of x in this situation? Over here. This is cubic because p of x was cubed. This is x cubed plus 2x squared minus x minus 2. Equal a linear times what will give you a cubic? A quadratic. So q of x, you'll know the other factor is a quadratic. That's all you know. You don't know what it is specifically, but you do know it's a quadratic. Okay. Keep going. Example 8, what is the value of k for the polynomial expression x cubed plus kx squared minus 5x minus 6 if x minus 2 is a factor? Is a factor, you have a division. Think about factor theorem. How do we write factor theorem? How do we check it? Well, we look at the binomial x minus a, and we know a is opposite, so a is 2. That means if it's a factor, p of 2 must equal 0. That's how we write the factor theorem for this question. It's different for each question because this number changes depending on the binomial that you're using. So now here I can expand by replacing number 2 in every single x of p of x. So we can write it as 2 cubed plus k times 2 squared minus 5 times 2 minus 6, and it must equal to 0. Because we know that x minus 2 is a factor. We don't have to check it. The question tells us that. Then we have 8 there from 2 cubed plus 4k minus 10 minus 6 equals 0. All the like terms together here, we have negative 16 plus 8. What does that equal to? Negative 8. And then we can add 8 from both sides. 4k equals 8. And then how do we eliminate the 4 times k? Divide by 4 both sides. K is 2. And the last theorem, the integral zero theorem, page 28. Now, when you're asked to, and you will be asked to, when you're asked to find all of the factors of a certain polynomial, and we will go as high as polynomials of degree 5 to factor, you will not know what those binomials will be, and you have to start somewhere. And this theorem tells you sort of where to start and how to get to your first factor. Once you have a factor of one of the polynomials, you can use division, find the quotient, take that quotient and factor it further in the same manner. But you do need the starting point to help you continue on. We don't have shortcut methods for any polynomials larger than the cubic polynomial. We know how to factor linears, which is just GCF factoring, straightforward, the simplest kind. We know how to factor quadratic trinomials. I reviewed with you today those 2 ways when you have either 1 in front of x squared or a number in front of x squared. So we have ways to factor those types of polynomials. But higher than cubic, so cubic, quartic, quintic, the 3 kinds that we're going to do, we don't know, okay? Either you do trial and error by splitting the terms and see if you can group them 2 by 2, which I sometimes see in your work, and I know it's copied from ChatGPT or from one of the tools, because yeah, it will show you that they will show you how to can group them. But it's really unlikely that you can see those groups by yourself because there's not a specific way to find the groups. So our way of finding all of the factors is using this theorem, the integral zero theorem. Now it does have a fancy name. I'm going to tell you what those words mean. Integral comes from the word integer. Okay, so integral from the word integer. That means you're going to find this 0, which is going to be a solution to the corresponding equation. Or sometimes we call zeros a solution to the corresponding equation, polynomial equation. Or sometimes you call zeros the x-intercepts of a function, polynomial function in this case, or the x-intercepts. Corresponding you can do without these notes. I'm just telling you where the words are coming from, why they call it like that, okay? But basically, this theorem helps you start finding your first factors. So it's a tool to find the binomials of the form x minus a. So we're only looking for these factors. We don't have tools for other kinds of factors, because they may exist. The goal is to reach a quadratic, because once we have a quadratic as one of our factors, we can use quadratic methods to factor further, right? But up until then, we're stuck with this method, okay? So how does the theorem work? You will be looking at the free term. I wrote it here fancy, but you'll be looking at the free term, list all of the factors of the free terms, like positive and negative 1. And then all of the numbers that will divide negative 6, basically. Positive negative 2, positive negative 3, positive negative 6, okay? So all the numbers, the factors of -6, if you think about them as groups. And then one of these numbers will be part of the binomial. So is it, if you take +1, is it the a equals 1, meaning is it x minus 1, my factor, right? I'm checking that. I will be checking that with this theorem, okay? And then you take the -1 on this list. If a is -1, is that going to be x plus 1, my factor, and so forth. There you go, sorry. So in this list are the possibilities. Doesn't mean that all of them are factors. You have to go through the list to see which ones are the factors. Now, how do I check if a binomial is a factor? We have to go back to the factor theorems, right? We have to plug it in the factor theorem, and we want to make sure we get 0 once we calculate that value. If we're not getting 0, it's not a factor. Cross it over, move on, because that's what you're doing. You just keep checking to see what is that first factor. Okay, so theorem here, let's fill in the blanks, and we're going to go back to the example. If x minus a is a factor of a polynomial p of x with integral, again, integer coefficients, then a is a factor of the polynomial. Oh, sorry, if a is the factor of the free term, because you're taking it from the preterm from here, of a0, which is the free term. So this a from here will be one of the factors of the free term. Let's get started. So we take the free term, we list the factors. If you're working with 50, positive 50, you're not going to list all of them, but just the first 5. If you ran out, then you can still add some more, you know, but don't waste your time to like list all of the factors of the free terms, okay? But that's what it's coming from, yeah.
Just basically like one, right?
Yeah, you need 1 to start, yeah, and then we're gonna continue on, yes, okay. So we take the free term, we find some factors, the first in the list. This was the shortest, very small number, so I was able to find all of them. And then I start usually systematically with the first one. So in the list, positive 1. I'm checking with the factor theorem. Check with factor theorem, which says P of 1 equals what? 2 times 1 cubed minus 7 times 1 squared plus 5 times 1 minus 6. And I'm calculating that. 2 times 1 minus 7 times 1 plus 5 minus 6. That's 2, that's -7, and that's -1. 2 minus 7 minus 1, is that equal to 0? No. I like to just write not equal to 0 once I narrow down to a short enough calculation that I can tell if it's 0 or not. You know, I don't have to calculate. It's just a waste of time. Okay. So now that means this is no good. The binomial x minus 1 is not going to be a factor of the polynomial because the factor theorem checked it. It's not, okay? Then I go down this list here. I take -1 and check that one. So check P of -1. 2 times -1 cubed minus 7 times -1 squared plus 5 times -1 minus 6. Okay, go ahead, calculate. Don't have to wait for me. You can see what I'm doing, right? So 2 times -1 from -1 cubed, -7 times +1 from -1 squared, and then minus 5 minus 6, -2 minus 7 minus 5 minus 6. Is that equal to 0? No, because they're all negative. So I don't stop and like, okay, what is it? No good. All I need is to figure out, is it 0 or it's not 0, okay? If it's not 0, move on. So no good. Then what do I do next? Go to this one is no good. Not positive or -1, no good. So move into the 2's now. Start with either -2 or +2. It doesn't really matter. So I'm gonna go with positive because that's what I did for the ones. So A equals 2. That means I'm checking P of 2. 2 times 2 cubed minus 7 times 2 squared minus plus 5 times 2 minus 6. 2 times 8 minus 7 times 4 plus 10 minus 6. We have 16 minus 28 and then plus 4. Is that equal to 0? No. A equals -2. P of -2. 2 times -2 cubed minus 7 times -2 squared plus 5 times -2 minus 6. I remember these are all negatives, right? So this one is not 0 for sure. Twos are no good. Moving on to the threes. So A equal 3. I have a good feeling about this one. Yes. 2 times 3 cubed minus 7 times 3 squared plus 5 times 3 minus 6. 2 times 3 to the 3 is 27. -7 times 9 plus 15 minus 6. 2 times 27 is 54 minus 7 times 6, 63 plus 15 minus 6 is 9. 54 plus 9, 63, right? 63 minus 63 is 0. What does this mean when you get the factor theorem checked equal to 0, right? That means we have no remainder, meaning the binomial x opposite sign, so -3. So x minus 3 is a factor of 2x cubed minus 7x squared plus 5x minus 7. So if I take this divided by x minus 3, I will get a polynomial answer and no remainder to it, right? So just a simple answer. Questions? But that's how the theorem works, okay? You take the free term, okay, and that's where you're choosing your A's from the free terms factor. So list all the factors of the free term and then check each of them from the beginning with the factor theorem to see if one of them is a factor, right? And then once it is a factor, once the question tells us to factor it completely, we have to do other things, okay? But this is just so you can see how it works. We have more examples. Yeah. Example 9, I only did find one factor, so one binomial factor, so you can see how you find that first one. Example 10 will be something different. It says factor the polynomials below completely. That means we don't stop, right? We keep finding all the factors. So in the end, we end up, for example, for a quartic, like this one, x to the 4, so something that's quartic, you can have x minus a times x minus b times x minus c times x minus d. So basically you can have 4 linear binomial factors, right? Because it's x times x times x times x, it has to give you your x to the 4 back, okay? But you can also have something like this, x minus a squared, and then x minus b times x minus c, because this is squared, so you have 2 x's from there, x cubed, x squared, and then xx. You still have a quartic back, right? So the combinations can be different. It doesn't have to be all of those, okay? So we'll do a few examples so you can see how the factoring completely looks like. So factor g of x equals x to the 4 minus 3x cubed minus 7x squared plus 15x plus 18 completely. And it's gonna be about this on the page, so you see how to organize yourself, okay? And then for the next one, not so much. Yeah, this one is very long, okay? So first step is look at your free term, 18, and list the factors of 18, both positive and negative, because you're looking for integers. So positive -1, positive -2, divides by 3 as well. So 3, and then 6. And then you can just do ... Hopefully in the first 3, you find your first one that just starts the process. Okay, the first one, a equals 1. Our polynomial is called g, not p of x. So we can just say g of 1. This is a name for it. That's not a big deal. P or g or h or k. And then we're just going to replace all of the x's with 1. So we're checking the factor theorem. 1 to the 4 minus 3 times 1 cubed minus 7 times 1 squared plus 15 times 1 plus 18. It's 1 minus 3 minus 7 plus 15 plus 18. Not 0, because look at all those big positive numbers and the small negative numbers. It's not going to make up to be equal, right? To make it 0. So you can just write this not equal to 0. So I'm not going to get the x minus 1 as a factor. So that's gone. Let's check. A is -1. So g of -1. I'm going to switch colors so sometimes it's easier to see or to copy from far away. So we have -1 to the 4 minus 3 times -1 cubed minus 7 times -1 squared plus 15 times -1 plus 18. +1, 3 times -1 minus 7 times +1, -15 plus 18. 1 plus 3 minus 7 plus 3. Plus 18 minus 15. I feel like I missed a number there. Which one? One more time. -1 to the 4, -3, -1 cubed, -7, -1 squared, plus 15 times -1, 1, -1 plus 3, good, -7, -7, -15 plus, yeah, it's good, right? Is it equal to 1? Oh, but why did I get 0 for the other one? Did I make a mistake in the other one? -7. Yeah, it is 0, right? So -7, 6, 1 equal to 0. I don't know why I didn't see it. Today my numbers are just like jumping out of the page for me. Okay, so we have here 4, here we have -4, so -4 plus 4 equals 0, right? So what do we say when we have the factor theorem that equals to 4? Well, we're looking at the binomial, which is the binomial x opposite sign plus 1, and this one is a factor. That means we found one of these first factors. If I want to factor completely, I found the first one in the list, okay? Now, the rest of it, I don't know. So I will have to now do synthetic division to find the quotient of division, okay? So let's do that, synthetic division. division. You take all of the leading coefficients and there you go, you have some practice before your quiz with it. Divide by x plus 1, that means here I put the -1, drop the first number, and then multiply with the number answered there, and then add vertically. -1 times 1 is -1. Add vertically, -4. -1 times -4 is +4. Add vertically, -3. -1 times -3 is +3. Add vertically is 18. And -1 times 18 is -18. Add vertically is 0. Remainder. So you should get 0 as a remainder because we already checked, right? We already checked that we get the 0 as a remainder. This is just to get the quotient, okay? Now what's the quotient? 3 term plus x. Now increase the power, x squared to the left here, and to the left more, x cubed. So far, g of x, which is x to the 4 minus 3x cubed minus 7x squared plus 15x plus 18 is what? Equals when we divided by the first factor, x plus 1, and this quotient, x cubed minus 4x squared minus 3x plus 18, okay? So we did one factorization. We pulled out an x plus 1 out of it. And we were left with now a cubic. But that doesn't mean we factored it completely, right? Recap. Our job is to factor a polynomial completely. We start with the free term, and the goal is to find the first factor. That's our first step, okay? So from the list of the factors of the free term, we start checking and we find the first factor using the factor theorem. Once we found the first factor, we use synthetic division, step number 2, to figure out what's left when we divide by it. Okay, we should be having no remainder when we divide by it because we already checked that with the factor theorem. Now we're going to be left with another type of polynomial. In this case, we only reduced it by 1 degree. So we started with the quartic, we reduced it by a linear, we're left with the cubic, right? The cubic also is a polynomial that we don't know how to factor, right? Without this method. So we have to take now this polynomial, its free term, and restart the process, right? And find the first binomial x minus a, that's a factor, and then synthetic division, and then moving on. But once we reach quadratic, then it's quick, because those methods are faster, okay? So now this polynomial, that becomes our p of x. P of x, we have to factor this. Factor this now. The free term is 18, so basically the same thing. So positive, -1, positive, -2, ... Now, we already checked the 1, right, in the original one. If 1 didn't work for the original polynomial, it won't work from here too, because it's still part of the original polynomial, even though it's over here split up, right? So don't check the factors that you already checked previously, but you can check the same factor again, because if it happens again, it's only going to become something like this. It's going to be something that's now squared or cubic because it happens multiple times, okay? So I would always check again just to make sure that I find it, because that's the easiest thing I can do. So I would check again. A equals -1, just to make sure. And then we move on down the list again with 2 and 3 and so forth. But don't check the ones that didn't work. Only check again the ones that just worked before. So we're gonna take this polynomial coefficient. So actually we're gonna get there when we divide, but we need to check it. So P of -1 is -1 cubed minus 4 times -1 squared minus 3 times -1 plus 18. -1 minus 4 times 1 plus 3 plus 18. We have -1 minus 4 plus 21 is not equal to 0. So it doesn't happen again. Then A equals to P of 2. In here, remember we're checking this quotient. 2 cubed minus 4 times 2 squared minus 3 times 2 plus 18. 8, 4 times 4, 16, so -16 minus 6 plus 18. -22, +26, so that's not equal to 0. A equals -2, P of -2. -2 cubed minus 4 times -2 squared, so forth. We get -8. Here's +4 times -4, -16, +6, +18. And these ones will equal to 0, right? So x plus 2 is the second factor. Once you found the second factor, you take this quotient from here and you divide it into the factor, because now you want to split up the cubic into smaller and smaller polynomial. So synthetic division is the fastest one. You take these coefficients from here, or you can take them straight from here, right? From the bottom to the same one. So you have 1, -4, -3, 18. And in the left here goes this A, -2. Drop the 1. Multiply. And put the answer then, add vertically. -2 times 1 is -2. Add vertically, -6. -2 times -6 is +12. Add vertically, 9. -2 times 9 is -18. Add vertically is 0. You've got to get the remainder of 0. And now we got pre-term 9. And then we have the -6x middle term there and the x squared. And we reach the quadratic. So far we have what? So far, our g of x is that, right? So x plus 1. But now this term here is the x plus 2 we just found, and this quadratic. We have 2 linears and 1 quadratic. When you reach a quadratic, you don't need to use this method anymore. because we have a better way of factoring quadratics, right? Free term here. What are two factors of 9 that add together to -6? -3 and -3, right? So this is the direct kind. We just need to write. Let me just copy the first two there, x plus 2. We just need to write two brackets with x's in them to factor this last one here. And then we just find the factors of the free terms and plot them straight there in the brackets. Like that. And now we factor our our quartic polynomial completely. This is a fine way to write it first to see what we got. But every time you have a binomial that's the same, you're going to put it together because repeated multiplication is a power, okay? So we're going to rewrite it as x plus 1 times x plus 2 times x minus 3 squared, because it's happening twice there. Done. And it is important later on when we are graphing these polynomials, if it's squared or if it's 1, if it's cubed, it has some meaning in the way we sketch it. So no, I don't think so either. And yeah, some of them are long, some of them are shorter. You'll do all kinds. The next one is going to be shorter. So, f of x is x cubed minus 3x squared plus 7x minus 10. The same question, factor it completely. And this is going to help us remember now the steps, okay, because it's a bit shorter. So what do we do when we have to factor completely a polynomial that's higher degree than 2? We take the free term and list its factors. Plus minus 1, plus minus 2, plus minus 5, and plus minus 10, right? Anything else we left out? No, it's the short one because it's a small number that we factor. And then we look down the list and we're going to use the integral zero theorem to find the first binomial that we can divide by to reduce it. So in the list, we have 1, so A is 1, and we do f of 1 to check with the factor theorem. 1 cubed minus 3 times 1 squared plus 7 times 1 minus 10 is 1 minus 3 plus 7 minus 10. Not equal to 0. The negatives are bigger than the positives. How about -1? Plug in -1 everywhere there's x. And then we get -1, -3, minus 7, minus 10. They're all negative, so not equal to 0. And then how about 2? We go down the list. F of 2. 2 cubed, and so forth. And we get 8 minus 12 plus 14 minus 10. This is close. So we have 22, -22. So this one equals to 0. Meaning x, what is our factor? X minus 2, you got it. Synthetic division, 1, -3, 7, -10, and then 2. 2 times 1 is 2. Add vertically, -1. 2 times -1 is -2. Add vertically is 5. 2 times 5 is 10 equals 0. It's gonna be 0 because you already said it's gonna be 0. And we are left with our quotient there. Free term, middle term is -1x, and then x squared. This is also a quadratic, so that's why it's shorter, because once you reach the quadratic, you're not going to do this longer version. So far, f of x is the factor x minus 2, and the answer to that division, x squared minus x plus 5. This is a quadratic. You're just going to use quadratic methods to see if it's factorable. So we have free term 5. Can I find 2 factors of positive 5 that add up to -1? No, we've done an example with 5 rows, -5, I think, right? We only have 2 possibilities, +1, +5, doesn't add up to -1, or -1, -5, doesn't add up to -1. So therefore, no factors possible. So this is our complete factorization, because we cannot factor it further. Make sense? Um, 10 minutes break. Okay. And then polynomial equations. So 3:30. Polynomial equations. Equations are equalities that include unknowns. We may have equations with one unknown, usually known. This unknown is by using the letter x, but we can have 2 or more unknowns. This is page 32. What does it mean to solve the equation? A lot of the times, if I just ask students solve the equations, I got sometimes in the past confusion. I didn't know what to do. Was I supposed to do this? Was I supposed to find the x? Well, when you are asked to solve an equation, yes, you are supposed to find what value of the unknown you can replace it with so that equality makes sense. It's true, right? So you have to find the unknown. So solve the equation as a vocabulary explanation there means you find the values that will replace the unknown or unknown so that the equality is true. So far, up to this grade, you have seen polynomial equations before. So you've seen a linear equation, so you should know how to solve a linear equation. You have seen quadratic equation, and you should know how to solve quadratic equations from grade 11. That's where you learn that. When you are solving quadratic equations, there's 4 different ways to solve them. You can solve them all by using the quadratic formula. So any kind of quadratic, if you have it in general form, you know, we can see the coefficients A, B, C, you can solve it with quadratic formula. The quadratic formula is in your formula sheet, and you can have it for your tests, so you don't have to memorize it. We will be using it sometimes, I think today or next class, but you will see it at some point, a revision of it. You can solve some of them, and our goal is that most of them we could solve it with this method using factoring, or the factored version of the quadratic. And some you can solve them by using square roots approach. And then also you've learned in grade 11 that you can solve them graphically. looking at the graphs of their corresponding functions. We are not going to do the graphical approach because we don't have graphing calculators. Not all of us. We're not required to have it. So, okay, the focus of our lesson is to use factoring skills, the ones with higher degree polynomial equation skills, to solve polynomial equations up to degree 5. So you are sometimes going to be given general form of an equation. So everything up to equal is the same thing as a polynomial that we have worked with so far. But because now we're working with polynomial equations, it will be equal a number, okay? Now what you want is to make it equal to 0 before you can start solving for it. So move all of the numbers on the left-hand side. So add, subtract to both sides to have equal to 0 to get started with the process of solving the equation. So in its most basic form, you would have a polynomial expression equal a 0. If it's not 0, you make it 0. And then the easiest way to solve it is have it in factored form. And we have seen the skills of how to factor a polynomial. And once you have each of those factors, you can take them, equal them to 0, and solve within that smaller bracket. Pretty easy, I promise you, it's not hard. So a polynomial equation, once we solve it, it can have up to n solutions, where this n is the degree of the polynomial. So if I have degree 4 polynomial, I can find up to 4 different solutions. But I can also find 2 of the same kind and 2 different, okay? But up to 4, not exactly 4 all the time. If it's degree 3, I can find up to 3 solutions. That means I can find 1, 2, 3, maybe even none, you know, but I cannot find 4 for a degree 3 polynomial, okay? The roots, and I have in the brackets, there are other names for the same thing. Solutions, zeros. So the solutions of polynomial equations are all real numbers. So any number you can imagine can be a solution. So any number from the number line, that's a real number. And the roots of solutions or zeros of a polynomial can sometimes be multiples. A multiple solution. So for example, here in this quadratic equation, because you have x minus 1 squared, that just means x minus 1 times x minus 1 equal to 0. What kind of x can I put here so that this is equal to 0? What do you think? 1, right? Because if I put here 1, then I have minus 1, this bracket is 0, right? Then it's going to make the whole thing equal to 0, then the equality is true, right? The way to get to these ones, like in this situation, you just say x minus 1 equal to 0 and solve for x here. Move the negative 1 on the other side, so x equals 1. We call this method splitting and solving. So splitting the individual brackets, equal them to 0 and solve inside each of these brackets. And we call this a multiple or the multiplicity of 2 because of this 2 here. So I will get a solution of 1 from the first bracket here, but I will also get solution 1 from the second bracket. But it's not a different solution because number 1 is the same thing. Either you get it from the first bracket or from the second one, right? So you get it twice. So you can just say x equals 1 and you just put multiplicity 2 beside it. And in this example here, when you have a cubic, x plus 1 cubed, this is x plus 1 times x plus 1 times x plus 1 equals 0. That's what cubing means. Then you can just take the first one here, x plus 1 equal to 0. What is x equal to? Negative 1. And then you can take the second x plus 1 and repeat the same process if you want, but notice it's the same thing, so you don't really have to. All you have to do is notice it's going to happen 3 times. So that's called a root or a solution. That's a multiplicity of 3, an odd multiplicity. It will mean something for us again later on if it's odd or even. Okay, but yeah, it happens 3 times. Okay, let's solve some equations to finalize our notes. Solve the following polynomial equations. The first one is the review because it's a quadratic. So I can solve this quadratic equation, the x squared minus 3x minus 4 equals 0, using quadratic formula, factoring, and even if I want square roots, but that's more difficult and I shouldn't do that. The first thing that I would do is skip quadratic. I would go straight to factoring because if I can factor it, it's so much faster, okay? If I cannot factor it, then I would use quadratic formula, okay? So I go to -4. Can I find 2 factors of -4 that add up to -3? -4 times 1, right? Add up to -3. That means my equation would look like this. 2 brackets, each of them would have x in the bracket, and then I'm going to use the factors inside those brackets. X minus 4, x plus 1 equals 0. And now, once you have it in factor form, we can do what we call splitting and solving. We're going to let x minus 4 equal to 0. Solve for x there. That's our first solution. And then we're going to let x plus 1 equal to 0. And that gives us a solution at x equals -1. And you can check it as well. You can check your solution. But does it mean that x equals 4 is a solution? That means if I put 4 here in every one of the x's, and I calculate with those 4's in there, I should get equal to 0. Because that's what I started with. It should be equal to 0 if I found the solution. So let's check. 4 squared minus 3 times 4 minus 4 equals 16 minus 12 minus 4 equals 0. So it checks, right? It gives me equal to 0. And the same thing for the other one. -1 squared minus 3 times -1 minus 4 is 1 plus 3 minus 4 equals 0. So also checks, right? Every time you're solving an equation, you found solutions. If you plug back into the original equation, you should get a true equality. If you don't get a true equality, that means it's not a solution. You got something, maybe a missed step there and you messed up solutions, right? That's why checking is important. Do you have to check all the time? No, but if you're not certain, then you would check. Moving on to a cubic, because I have here 1 and I have here 2 for each of my binomial factors, but it's already in factored form, right? So basically, I'm not giving you any factorization to do. It's already factored. All you got to do is skip to the step, splitting and solving. So you let x plus 2 equals 0. X equals -2. That's my first solution. And then in the second bracket that's squared, you're going to let x minus 3 equal to 0. X equals 3. And you can, if you want, I'm not going to write it as wrong if you don't. That's a multiplicity of 2. This is only going to be important in lesson 3 when we graph polynomial functions. Right now, if you write it or not writing it, it's still the same solution. Okay, And the last one is the one that you normally would get for this part of the notes is solving an equation that's higher degree than 2. So 3, 4, or 5. Yeah,
What's that, when you solve that, that is, there's two letters, what that is?
that's multiplicity of 2, M2. M for Matthias, Mike. Okay. So x cubed minus x squared minus 7x equals -3. We know this is not equal to 0, okay? All of these ones don't work. Factorization, you know, the starting of an equation, if it's not equal to 0. The only way you could solve this one by not equal to 0 is by graphing it, okay? That works, okay? But we have to move the -3 on the other side to even start this question. So I would add 3 to both sides, and it's gonna give me x cubed minus x squared minus 7x plus 3 equals 0. And now, on the left-hand side, I have a nice clean cubic polynomial equal to 0. What I have to do is factor it completely, and then I want to end up with nice factors in the binomial forms, hopefully, okay? And then I can take each of those, equal them to 0, and solve the equation, okay? So first step, step 1, factor. We have a cubic, so the only way we know how to factor is look at the free term, which is 3, plus minus 1, plus minus 3. The list is not too long, right? So not a lot of checking to do. Yeah? Okay. A little bit of a long one, huh? Okay, so we have 1 cubed minus 1 squared minus 7 times 1 plus 3 equals, I'm checking obviously a equal 1. We have 1 minus 1 minus 7 plus 3. Is that going to equal to 0? No, right? But not a factor at x minus 1. How about a equals -1? -1 cubed minus -1 squared minus 7 times -1 plus 3. -1, subtract 1 plus 7 plus 3. Not going to equal to 0. A equal 3. 3 cubed minus 3 squared minus 7 times 3 plus 3. We have 27 minus 9 minus 21 plus 3. Equal to 0? -30, positive 30. Equal to 0. Yes. Therefore, since the factor theorem application showed us it equal to 0, means that x minus 3 is a factor. And you already have a solution from here. What's the solution from x minus 3? The first solution will be x equals to 3, right? So we're going to get there until once we have all of the factors. But you can see it already. Cubic divided by a linear is going to give us a quadratic. Once we get to quadratic, we're going to try the factoring method to factor it. If not, we're going to use quadratic formula. Okay, so let's try first to get the quadratic. Synthetic division. So 1, -1, -7, and 3, and then 3 on the left. Drop the 1, and we start. 3 times 1 is 3. Add vertically, positive 2. 3 times 2 is 6, and vertically -1. 3 times -1 is -3, 0. So far, we have our equation looking like this. X minus 3 from here, and then x squared minus positive 2x minus 1 equal to 0. That's our equation. Can we factor this quadratic? Because if we can split up the quadratic into two linear binomials, and that's going to be a little easier to solve. Can I find two factors of -1 that add up to 2? No. Now, this is why I put this example in your notes, to show you that just because you cannot factor it doesn't mean there's no solutions this time, because you can still find solutions by using quadratic formula, okay? Now let's solve for this equation. We cannot solve it with factoring. On the left-hand side, we can let x minus 3 equal to 0, find the first solution at x equals 3. On the other side, we have x squared plus 2x minus 1 equal to 0. But since it's non-factorable, quadratic formula to get our solution. Well, the quadratic formula scares people. It looks messy, but it's quite easy to apply. Okay, it looks like this. You might get up to 2 solutions. So you sometimes write it like this: x1 comma 2, and it's minus b plus minus square root of b squared minus 4ac divided by 2a. Where a, b, c are the coefficients of the quadratic trinomial. So that's where a is, that's where b is, and that's where c is in that formula, okay? So a is the coefficient of the x squared term, that's 1. B in the situation is positive 2, and c is negative 1. This formula is given to you. So you just look at your formula sheet if you need it, and just find ABC for your quadratic and apply it, okay? Now let's practice with the application, because you might not have seen it since grade 10. So we have to solve for this. We have x, and then we plug in. Everywhere you see B, A, C, put the bracket around it, because sometimes you have 2 negatives, one from the formula, one from the actual value, and then you don't want to confuse them, that they're the same negative, okay? So here I put the negative from the formula, I put a bracket for the B, and plug in inside the bracket what B is, so 2. I'll just put it in there like that, okay? And I have plus minus square root of, and I know it's going to be something b squared minus 4, and I put brackets for a, brackets for c, like that. 2 times and brackets for a. B is 2, a is 1, c is negative 1, and then 2a, so 2 times 1. Simplify now and just reduce it, simmer it down to something nicer looking than that. Minus 2 plus minus square root of 4 plus 4, which is 8. 4 from here to square. Negative 4 times 1 times negative 1 is positive 4. So 4 plus 4 is 8. And then 2 times 1 is 2. Now I can make that even nicer looking. So let's do that. 8, square root of 8, square root of 8 is square root of 4 times 2. Right? Because 8, I can write it as 4 times 2. And since 4 is a perfect square, I can evaluate it outside of the square root, right? I can do square root of 4. So basically, it can split up like that. What's square root of 4 equal to? 2. And then square root of 2, I cannot evaluate. So I wrote it as a mixed radical, okay? Now, why did I do all that work? Well, because the 2, it will cancel nicely out of these. So factor it out. Remember, I told you can only cancel if it's a multiplication. So we can take the 2 outside. And we get 1 plus minus square root of 2. And then the 2 at the bottom. And now you can cancel the 2's. And our solutions are 1 plus square root of 2 and 1 minus square root of 2. Remember, our solutions can be any real numbers. So whatever that is, square root of 2 is about 1.7, so 2.7-ish. Or negative 0.7. Oh, negative. I forgot my negative here, right? Negative. Because this first term here was -2, so -1 here, -1, negative. Remember quadratic formula? How many of you remember this one?
-1 plus minus
This,
root 2.
this one, the 2 root 2. This is from here. I just took the 8, square root of 8, and I rewrote it like 2 square root of 2. So instead of that, I wrote that. That's factoring. Remember factoring from earlier today, the GCF? So I took a 2 out in front, and then I'm left with -1 plus minus square root of 2. Because here you can have negative, let's put 2 times -1, and here you have 2 times square root of 2. So you have a common factor of 2. You can put it in front, 2, and you're left with -1, and then square root of 2. Plus, minus, it's from the formula. I haven't done anything to it, so. This one? It's by factoring. Let me separate it a little bit more. So if you have 2 plus 2 square root of 2, this is common factor. So you take out in front, bracket, 1 plus square root of 2. Just that in our equation, it was plus minus, all it is, you know, yeah. And then we had a negative. So if you have a -2 plus 2 square root of 2, you can still take out the 2 out. What you're going to be left with is -1, right? And a negative square root of 2. -2 minus 2 square root of 2. If you take out a 2, you have -1. Positive, yes, 2 negative. Wait, where's my negative coming from? This is positive, and this is negative. Square root of 2. And now these ones, if you combine them, because you have a positive and a negative, you can just rewrite that as 2, -1, put them together, plus minus, square root of 2. It doesn't really matter if you write them together or separately. But I wrote them separately for you at the end, so you can see there's 2 solutions there. One when you add the square root of 2, one when you subtract the square root of 2. Does that answer your question, Mike? Kind of? Let's read them. So, about 4 minutes to 3. So right here, right? So this is where we stop, right? That's this is where you're good up to, right? Yeah. So -2 plus minus square root of 8 divided by 2 equals -2 plus minus, we're going to rewrite square root of 8 as 2 square root of 2. That's understandable for everybody, right? Divided by 2. And now at the top, I'm going to factor out, because you can see how 2 repeats, right? So I want to just cancel it out with the 2 at the bottom. And I'm not allowed to cancel here, 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 because then you're going to make mistakes when it's not everywhere. So I want you to first factor it out, because you can only cancel things that multiply. And right now, they're not multiplied, they're just plus, right? Or plus minus. So I'm going to take out the 2 from here at the top in front, and I'm going to factor it, okay? Now, what's left in the first here if I divide by 2 that I took out? Because remember, when we factor, we divide by the number we chose to factor, right? So here I divide by 2. It's going to be left -1, right? Plus minus, what's going to be left here if I divide by 2? Square root of 2, right? Okay, now I factored, I can cancel these 2's in front. Because now I have 2 times something, I can cancel the 2 at the bottom. And you're left with -1 plus minus square root of 2, and you can split it up into -1 plus square root of 2, -1 minus square root of 2, okay? Okay. This is it in terms of lesson for today. We can take 10 minutes break again, 3:10. We're starting our partial number 1. Which is going to be from lesson 1, synthetic division, long division, and 1 extra application. Make sure you have everything you need for your partial in your study sheet. Okay. If you still have some questions for me, ask me before you start. You can take until the end of class to write it, or just until you need it. Okay. So if you finish in 10 minutes, you can hand in. I may be able to mark it for you right away and give you your answer. If you take longer, that's fine too, you know, whatever you need. If you want to start a little later, don't give yourself less than half an hour though, okay? So if you want to start it at 4:30, that's fine too. It will definitely take you up to half an hour. So 10 minutes, 3, 4, 10.